Next, I'd like to talk about how we can use our elementary reactions to figure out our overall rate law and better understand the kinetics of our reaction. So, on slide 26, we're going to talk about validating mechanisms for two different cases. In our first case, let's say that our rate limiting step, or our RLS, the rate limiting step, is the first peak in our reaction profile. Okay, in this case, the rate is only affected by our first step. You can kind of think of it, this is our reaction coordinate, right, where we have our energy and our reaction coordinate, all right? As you can see, if our first peak is really big, right, it's kind of like that ride at Disneyland where you ratchet all the way up, and if it's the first peak, it takes you a really long time to get up to the top, right? That's our slowest part of the whole ride, but then everything after that is really fast as you cascade down the mountain, right? So whatever your biggest peak is, that's going to be your rate limiting step, okay? Now, if your rate limiting step is the first peak, that's going to be the one that dictates the kinetics of your reaction. So let's say that we have the two elementary steps of NO2 plus NO2 gives us NO3 and NO, right? That would be our slow peak in this process, right? Because that's our first reaction, okay? Again, that would be our rate limiting step. And then our second process is NO3 plus CO goes to NO2 plus CO2. And of course, since we're going downhill, it is our fast process, okay? Now, when we want to build our overall reaction, right, what we're going to do is, of course, we're going to cancel everything that we can. If it appears on the left, we can cancel it on the right, okay? So that leaves us with an NO2 because one of the NO2s was canceled. We add the CO. Again, basically everything to the left gets added on the left side of the arrow. Since the NO3 and the NO2 here got canceled, we only have one NO2 and a CO on the left. And then on the right, we have one NO and we have one CO2. Okay, this is our overall reaction. Okay. Again, we got our overall reaction by adding up our elementary steps. Okay. Now, in addition, notice that when we're looking at this, right, we have a large activation energy. That's the energy from the first trough right before the peak. So we have this right here up to the top of the peak. That's our first activation energy, or the energy needed to go over that barrier. And then we have a second activation energy, which is the energy from our intermediate up to the top of our second peak. Okay, and notice in this case that our activation energy 1 is much bigger than activation energy 2. Okay? Now, when that happens, when the activation energy for peak 1 is bigger than that of peak 2, the rate is dominated by the first reaction. Okay, we've sort of said that a bunch of different ways, right? I usually think about it, whatever the biggest peak is, that's my rate limiting step. That's the reaction. If it comes first, okay, if it comes first, then the rate is only affected by that step, okay? You can kind of think of it, right? If most of the time on the ride is at the very beginning, then that's the time that you remember because everything after that is super, super fast, right? If you have a bunch of little hills and it takes forever, right, then you'll remember the stuff that happens before it, and that becomes important, okay? But if your first peak is your rate limiting step, then that will be the only reaction that matters, okay? Now, when that happens, the rate is given by the first elementary reaction, which means that our rate law overall, I should say our overall rate law. That means that our overall rate law for this process will be dictated by the rate law of this elementary reaction. And what it will be, if you remember, we can write down our elementary reaction rate law by simply saying, okay, I know that I have an A plus an A, right? Those two species are the same, which means it's going to be the rate constant times my concentration of A squared, but in this case, A is NO2, so it's going to be the concentration of NO2 squared. All right, so that would be how we figure out our rate law based on a series of intermediate steps, or based on the elementary steps, our elementary reactions, if our rate limiting step is the first peak. All right, it's the first peak, it's dictated by the first elementary reaction. All right, now our second case appears on slide 27. All right. Slide 27. Terrible. Slide 27. Okay, now in this case, we have a fast initial step. Okay, and when that's the case, for case 2, and we have a fast initial step, here the experimental rate law or overall rate law cannot contain any intermediates. This is very important. Okay, so if we have a fast initial step, our rate law cannot contain any intermediates. Okay, now that means that we must eliminate our intermediates mathematically. Okay, so in the case where we have a fast initial step, okay, that means that we don't have this reaction profile, but instead our first peak is fast, right? So that means it must have a relatively low activation energy. Okay, so last time we saw that we had a peak like this where our first peak was big. In this case, where we have a fast initial step, we're going to have a small peak as our first peak, and then a subsequent peak is going to be larger, right? So we have our activation energy for that peak, and we have an activation energy for our second peak. Here, notice that our activation energy for our second peak is much larger than that of our first peak, right? Now we could have multiple other peaks. Whatever your biggest peak is always going to be your rate limiting step, right? So that's our rate limiting step. And everything that happens before the rate limiting step is going to be important, okay? So in our last case, there was nothing before a rate limiting step. Here we have an extra peak. That's a fast step, which occurs before our rate limiting step, okay? Now, in this case, notice that an intermediate appears in between our first peak and our second one. And since it happens before the rate limiting step, it's going to show up as we begin to do our calculations, okay? But it's important to note that our experimental or our overall rate law will not contain any intermediates. So when we see our intermediate, we're going to have to calculate a way to evaluate it with some of our other terms, okay, to get rid of it in our equation, okay? So in this case, this is what our reaction coordinate will look like. Now, let's say that we have NO plus NO. Now, since we have an intermediate, all right, that means that it can sit around, since this is a fast process, right? You can imagine that you can go back and forth over that little peak pretty easily. It'd be very difficult to go back and forth over this big peak, but it's relatively easy to go back and forth over the little one, okay? So, before I show you the reactions, I should say that when we have steps before the rate limiting step, okay, then equilibrium is established. Okay, and equilibrium, and we'll talk about this when we get into our next chapter, but equilibrium is basically saying that you can go back and forth to form some sort of balance between the process going forward and the process going backward. Okay, you can imagine that it takes a little bit of energy to go up, and you could slide back down the mountain, and then it requires more energy to go up, and so there's an equilibrium, a push back and forth as you go over that first peak until you get enough energy to go all the way over. Okay, so since we establish an equilibrium here, that means that our first reaction will be an equilibrium reaction, which we denote NO plus NO. We have a forward process and we have a backward process. Okay, we will have a K1 going forward, and we will have a K -1 for the first reaction going backward. Okay, and it forms N2O2. Okay, the K1 is the rate constant going forward, and the K -1 is the rate constant going backward. Okay, it's almost like we have two mini reactions in this elementary reaction. We also are going to have the second reaction, which is taking us over this second hill, okay, which is N2O2, let me rewrite that, where we have N2O2, and it goes with oxygen forward, and it has a K2. That's the rate constant for this second reaction going forward. That K2 goes to 2NO2. Now, as we said before, since this peak is small, it's going to be relatively fast. Okay? This second peak is our slow step and is our rate limiting step. Okay? So now we have 3 rate constants, 2 reactions. Okay? Now, if the reaction is going backward, right, that means that this will be our reactant that we are using. Okay? And these would be the products. Okay? Going forward, we have these two, the NO and the NO, as our reactants, and this being the products. So the forward reaction has these as the reactants. The backward reaction has this as the reactants. Okay? Now, as we look at these, all right, we would probably think let's see. All right. Here we notice, right, that we have the NO2 formed in the middle, right? Since it's formed in the middle and consumed before the end, then that means that this is a intermediate. Okay? That's the species that exists here in that little trough. Okay? Because remember, these are our reactants, our intermediates, and our products all the way on the right. Okay? So that's our intermediate, N2O2. So that means it can't appear in our rate law, right? Because we would have initially thought, okay, if I look at this, I could say, oh, I have a rate, and it equals K2, right? Because if I took my rate limiting step, I would just say, oh, okay, I use my elementary, and it has K2, and then we have N2, O2 to the first, right? And then we have O2 to the first, okay? But notice, even though this is our rate limiting step, and this is the rate law dictated by our rate limiting step, okay? Notice that we have this intermediate here. And what was our rule? That it cannot contain intermediates and we have to eliminate them mathematically, okay? So this is our rate law for our second elementary reaction. We can't use this as our overall, okay? So we still need I'm going to erase this. Here, we still need to consider the equilibrium of the first elementary reaction. Okay? So let's write down our rate laws for our first elementary reaction. Notice that we have one going forward, okay? And for the one going forward, we have rate is equal to, let's see, we have K1 times NO squared, right? Because we have 2 NO and we have our K1, that's going forward. We also have a rate going backwards, which is equal to, so this would be our rate 1, this would be our rate -1, right? This would be K -1 times my concentration of N2O2 to the first, okay? And then I have my rate law for the second reaction, right? So my rate 2 is equal to K2 times my concentration in N2O2 to the first times my concentration in oxygen to the first, okay? Again, where I've just taken the species, raised them to the number of times they appear, and multiplied it by the rate constant in the direction that I'm going, okay? So again, this first one came from NO and NO, so there are 2 of those, so I have NO squared, right? And then I have my K1 since I'm going forward. In the second one, I take this reaction and I'm going backward. So I've got my concentration of N2O2, it appears once, and I multiply that by my reaction rate constant going backwards, my K -1. Then I looked at my second rate and I said, okay, well, that's my concentration of N2O2 to the first times my concentration of O2 to the first, because I only have one of each of those, and I multiplied that by my rate constant there. Notice that there's not a backwards reaction for this process because that was our rate limiting step and we can't go back over that mountain, okay? So here are 3 elementary rate laws, all right? Now, at this point, we know that these 2 rates, those are for the same reaction, right? So that means that our rate, these rates here are equal, okay? So if they're equal, then that means that I can take these 2 reactions and say, okay, I have K1 times my concentration in NO squared, and that's going to be equal to K -1 times my N2O2. And that's because they are in equilibrium with each other. My rate going forward is equal to my rate going backward, okay? So they're equal at equilibrium, all right? So now I have this expression. At this point, I'm going to solve this for the intermediate. Okay, so my first step was to equate the rates. My second step is to solve for the intermediate, and in this case, I get my concentration of N2O2 is equal to K1 times my concentration in NO squared all over K minus 1. Again, just using algebra, I'm dividing both sides by my K minus 1. Okay, so now I have this intermediate. And then, as step 3, evaluate into the rate limiting step. Okay? Or the rate limiting rate law. Okay? So here was our rate limiting steps rate law. So I know that I have the rate 2 is equal to K2. Here's my intermediate. Here's my intermediate. I'm going to evaluate this in as my N2O2. So I'm going to plug this in, and so I have K1 concentration of NO squared all over K minus 1 multiplied by my concentration in O2 to the first. Now it's customary to group together all of the K's together. So I have K2 times K1 all over K minus 1 times my concentration in NO squared times my concentration in O2 to the first. This right here would be my overall rate law for this process, accounting for the fact that our rate limiting step was not our first step in the process, and that we had a fast initial step. All right? So again, I would take a look and review all of this stuff because it will appear on the quiz. All right? And good luck on your quiz today. If you have any questions, feel free to email me.